Hello friends, we welcome you all to the third session of Unit 2 Digital Logic and Data Presentation. So in today's session we will be looking at a brief recap of the previous session and we will be moving on to logic gates. We will be looking into types of logic gates and few applications of the logic gates will be seen in this session, and finally we'll be having a small MCQ session as usual. In previous class we had seen signal. A signal is simply a form of communication. So we had seen two types of signal. One is the analog signal and the digital signal. Analog signal was infinite with respect to time, that is, it was continuous and it was continuously varying with respect to time, whereas the digital signal was discrete within the time interval. We also saw the microprocessors or the control systems can understand only digital signals in the binary form. The analog signals cannot be directly fed into the microprocessors, hence they have to be converted into digital form. After processing, the signal from the microprocessors has to be converted back again into their analog form before they actuate the next stage or the hits out the display stage. So in this class we'll be looking into logic gates. We had seen control system which works based on signals. Signals may be externally generated or may be inputted into the control systems. Control system decides the next set of action based on the predefined condition. We had seen the washing machine example where the level of water is taken as an input to decide whether to fill the drum with more water or to stop the flow of water into the drum. The controller here is programmed to only give yes or no input, whether to allow the water into the drum or to stop the water flowing into the drum. So this simple yes or no decisions are taken by logic gates. Such operations are carried out by logic gates. Gates. Logic gate is called as the basic building block of digital electronic circuit. This is the basic building block. With this basic building block, the complex electronic circuits, as we have seen in the example of an ATM machine, washing machines, etc., various other applications are there. For all this, the logic gates form the basics. So we see there are three basic gates. Logic gates are classified mainly as basic gates, universal gates, and arithmetic gates. The basic gates are AND gate, OR gate, and NOT gate. These are the basic form of gates. And next comes the universal gates. NAND gate and NOR gate are called as the universal gates because they are called as universal because using these two gates all other gates can be realized. By using just the NAND gate I can obtain even the AND gate also, hence they are called as universal gates. Next comes the arithmetic gates. XOR and XNOR. X represents the exclusive. X means exclusive OR gate and exclusive NOR gate forms the arithmetic gates. They are called arithmetic gates because they are mostly used in arithmetic operation, addition, subtraction, multiplications, etc. How these are used, we'll be seeing it in this class. One example of this arithmetic gates forms the parity generator and parity checker, which we will be seeing in today's session. First, let us see the first type of basic gate, that is AND gate. AND gate accepts two or more input. It can take n number of inputs. For simplicity, we will consider only two inputs, that is A and B. When I say A and B, these two are signals. A is one signal and B is one signal. They are in digitized form. We must remember the signals are not in analog form, they are digitized form. It represents binary data, either 0 or 1. The output is high when both the inputs are high. This is the main feature of AND gate. AND gate generates an high output when both the inputs are high. A and B both must be high. When I say high, they must be 1. Both must be 1. So output is 1 when both the inputs are 1. So that is the main feature of AND gate. The AND gate can be realized with two electrical switches in series. In this electronic circuit, we carefully observe that there are two switches in series. Suppose if an electric current passes through this switches, there is a load connected at the end. For this load to be on, current must pass through both the switches. Suppose let us say this is input A and input B. If this switch is open in the sense off, close means on. When the current passes, if the switch A is closed, current closed in the sense this is closed like this. Now it is in the open state, I have closed it. Current passes through. Next, the switch B is open. Now I will close. Now current completely flows through the circuit and makes the bulb glow. So this is the main principle of AND gate. In order to get the output high, that is 1, we have both the inputs A and B must be high. Suppose imagine both A and B are open, the current cannot pass through and reach the bulb, and hence there is no output. Output is 0. Imagine only switch A is closed and B is open. Now also the current cannot pass through and it is in 0 state only, that is low state. Hence the AND gate says the output is high when both the inputs are high. Both the inputs are high means both the inputs must be 1, both the switches must be closed, then only we will get the output that is high. Let us see the logic symbol and truth table of AND gate. We understood the feature of AND gate using this electrical circuit. Let us try to understand what is the logical symbol. The logical symbol in short represents this entire circuit. I have inputs A and B here. This input A and B, logically it is represented here. Must understand this is just the logical symbol. A and B is the input to this AND gate. AND gate is represented like this, just like the letter D, capital letter D. A and B forms the input. This is one input and this is the second input. Finally an output is generated which may be represented by Q, Y, C, whatever we are convenient with. The output inputs are A and B, so it can have n number of inputs but it will generate only one output. It can be Y, it can be Q, or it can be C. We know the logic for the output is both A and B must be I in order to get the output. The Boolean expression or the relation between the input and the output of AND gate is represented by the Boolean expression, that is output equal to A dot B, that is A multiplication B. So this is the Boolean expression, relation between the input and the output in the equation form is the Boolean expression. Using this we have drawn a truth table. Truth table is nothing but the tabularized form of outputs for all combination of input. We have all combinations of input written here. When A and B, all combination of input is taken and all possible output is written over here. Carefully observe, when both A and B are 0, that is switch A and switch B both are open, current cannot pass through, output is 0. Here we will see in the expression form A, B both are 0, 0 into 0 is 0. Now we will take 0 and 1, that is switch A is 0, B is 1. I am closing the switch B, but A is open, so current cannot pass through. Still the output is 0. Output is 0. 0 into 1 is 0. Next 1 and 0. I make this A 1 and B 0. A is closed but B is open, so still the current cannot flow through. The output is 0. Now finally, when I make both the switches 1 1, both the inputs 1, switch A is also closed, B is also closed. Now the current passes through. I will get the output. The bulb glows. This is the state high. Output is 1. 1 into 1 is 1. This is the output of AND gate. Next comes the OR gate. OR gate can also accept n number of inputs. In our example, we are considering input A and B. The main principle of OR gate is the output is high when any one of the input is high. Whereas with the AND gate, the output was high when both the inputs were high. But whereas in the OR gate, the output is high if at least any one of the input is high. Here we are able to see the truth table. We'll understand the truth table using the electrical circuit. The electrical circuit consists of two switches connected in parallel, whereas in the AND gate the switches were connected in series. In the OR gate the switches are connected in parallel. Since the switches are connected in parallel, suppose imagine the current is flowing through the circuit. It enters switches A and switch B. Suppose if switch A, now both are in the open state. Imagine if I close the switch A. If I close switch A, the current flows through and reaches the load and hence the bulb glows. Suppose when the current enters B, if I close B, then also the power enters, the bulb glows. So this is what the realization of OR gate is. There is output. Output is high when any one of the input is high. When switch A is closed, the bulb glows. If the switch B is closed, the bulb still glows. When both are closed, the bulb of course glows. But when both the switches are open, that is 0 0, first state, when switch A and B both are 0, the current will not reach the load, hence the bulb doesn't glow. So this is the first state. Only in this state the output is low. In all other state the output is high. The output is high when any one of the input is high. That is the main feature of OR gate. Close any one switch, we will get the output. This AND gate, OR gate output can be realized with two-way switches that we use it at our homes. A single bulb can be controlled using two switches. We can control with two-way switch from one point. If the switch is on from one side, still the bulb glows. If the same bulb can be controlled with the other switch, if we switch it off from here, still it gets switched off. So this is the classic example of OR gate. Next comes the NOT gate. NOT gate accepts one input and produces only one output. The NOT gate is also called as inverse gate. The main feature of NOT gate is inverse application. The truth table for NOT gate is shown here. When we already seen, it has only one input and it produces only one output. The output will be complement of the input. Suppose we say A is the input. If the input is 0, I get the inverse or complement of it 1. If the input is 1, we will get the output as 0. It just changes 0 to 1 and 1 to 0. That is called as complement or inverse. If A is the input, output will be A bar. That is the complement of A. So the output C is equal to A bar. So NOT gate is also called as the inverse gate. The logical symbol of NOT gate is shown here. It is represented by a triangle and a small bubble in front. This bubble is the inverse operation here. So this bubble represents the gate is of inverse type. The output is written here. For input 0, output is 1. Not A means not operated A. So for input 0, output is 1. For input 1, output is 0. So these three forms the basic logic gates. Next we will be seeing the universal gates, that is NAND gate and the NOR gate. NAND gate is also called as the universal gate. We have seen earlier also, NAND gate is called as universal gate because using this NAND and NOR gate we can realize all other gates. NAND gate can also accept n number of inputs. In our example we will be considering only two inputs, A and B. NAND is a combination of AND and OR gate. NAND gate is a combination of AND and NOT gate. AND gate, NOT gate combined to form NAND gate. It means the operation is same as the AND gate, but the result is complemented using a NOT gate in order to get the output which is just the inverse or complement of the AND gate. The Boolean expression will be, that is, the relation between the input and the output in the equation form is called as the Boolean expression. We have written here the C equal to A dot B is the Boolean expression for AND gate, but since we are combining AND gate and NOT gate, the result get complemented. A dot B whole bar. This is the result or the Boolean expression for NAND gate. Here the logical symbol of NAND gate is represented. It is same as the logical symbol of AND gate, but only thing we should observe, there is a bubble in front which gets the result complemented. The result gets complemented. This complement symbol is because of this bubble. Except this bubble, it is simply an AND gate. Adding this bubble, the result get complemented. If for example both the inputs are 0 0, by AND gate the output has to be, AND gate is A dot B, that is 0 into 0 is 0, but till here it is 0, 0 into 0 is 0, but after passing this bubble the result will be 1, that is the complement of 0 is 1. If suppose the inputs are 0 and 1, then also it is 0 into 1 is 0, output is 1, 1 and 0, 1 into 0, 0, after complement it will be 1. Suppose if the inputs are 1, let us say A, B both are 1 1 high input, A into B, that is 1 into 1 is 1, till here it is 1, after complementing it will turn 0, that is the inverse operation. This is the basic principle of NAND gate. The truth table for NAND gate is as shown below. As we discussed, the output is just the inverse of AND gate. If we remember the AND gate, 0 into 0 was 0. After complementing, we will get 1. 0 into 1 is 0. After complementing, that is the AND, we have the AND gate and a bubble in front. This bubble makes the output of AND gate to turn complement, that is NAND gate. So 0 into 1 is 0. After complementing, we will get 1 again. 1 into 0 is 0, but after complementing we will get 1 again. 1 into 1 is 1, after complementing we will get 0. If we remember well, this is exactly opposite of AND gate, that is the results are complemented. The output is high. Observe, the output is high when any one of the input is low. At least among both the inputs, any one has to be 0, that is low, in order to get the high output. If both the inputs are 0, then also it is fine. When any one of the input is low, still the result is high. When both the inputs are high, the result is low. Next is the NOR gate. It is also called as the universal gate. NOR gate also can accept n number of inputs. Here we are considering two inputs, A and B. The Boolean expression for NOR gate is as shown here. Before understanding the Boolean expression, let us understand NOR gate. NOR gate, as the name itself says, it is combination of OR gate and NOT gate. OR gate combined with NOT gate to form NOR gate. As we understood the NAND gate, in the similar way NOR gate also functions. The NOR gate output is same as the OR gate output with the output complemented. We know the OR gate. OR gate symbol, logical symbol is like this. We have two inputs, that is A and B. We are adding NOT gate to the OR gate. Hence we'll put a bubble. This bubble says the NOT gate. The output gets complemented. This is the NOR gate. Combination forms the NOR gate. But simply OR gate, when we say OR gate, this is the OR gate plus NOT gate. This is the NOT gate. Both combined to form NOR gate. We have two inputs and one output. Till here, till this position, what is the Boolean expression? A plus B. A plus B is the logical operation of OR gate. A addition B. But once this bubble is present, the entire result gets complemented. So this is the Boolean expression for NOR gate. So here it is shown. The logical symbol here we are able to see. The truth table of NOR gate is represented here. The truth table tabularizes the output for all combinations of input. The output will be just the inverse of the OR gate. Here we see the output is high when both the inputs are low. To understand this truth table, let us say this A and B are the inputs. We'll understand A plus B, that is the OR operation. OR operation, this is input, this is OR operation, A input and B input. Suppose all combinations 0 0 0 1. Now A plus B, 0 plus 0 is 0, that is only OR operation we are doing. So this is the logical symbol of OR, only OR operation we are doing. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is also 1. Here we do not have any carry representation because it is a single bit data. So hence 1 plus 1 is also 1. This is logical addition. Now we will get the complement. Till here we got this result, that is the same as OR gate. This is OR gate result, A or B. 0 plus 0 0, 0 plus 1 1, 1 plus 0 1, 1 plus 1 is also 1. Now we will complement the result, that is A plus B whole bar. Here we are adding a bubble. So to get the result C, C is equal to A plus B whole bar. That just the complement. 0 turns 1 and 1 turns into 0. This is the output of NOR gate. The output is high when both the inputs are low. The output is high when both the inputs are low. In all other cases, the output is low, completely low. In all other cases, the output is high when both the inputs are low. This is the fundamental principle of NOR gate. Next comes the XOR gate. XOR represent exclusive OR gate. It is one form of OR gate where the inputs are complemented. In the NOR gate we saw the output was complemented. In NOR gate we saw a bubble was added at the end in order to complement the output. But in XOR gate, the inputs are inversed. The inputs are inversed. If I say A and B are the two inputs, I'll make this input complemented before it enters the gate. So that is the main concept with the XOR gate. Here the output is high if any one of the input is high. Among the two inputs, if any one of the input is high, then the output will be high. The logical symbol is shown here. The logical symbol is pretty much similar to OR gate. If we remember, this is the OR gate symbol. Adding one more curve before will form the XOR gate symbol. This is the XOR gate. The output or the Boolean expression, if we remember, A plus B was the Boolean expression of the OR gate. Rounding this addition symbol will give me the logical expression for the XOR gate. So this is the XOR gate Boolean expression. The symbol, logical symbol is written here. Output is A XOR B. The circuit diagram of XOR gate is here. As we discussed in the previous slide, the inputs are complemented before it enters the gates. Here observe, A and B are the two inputs. Here I have taken in the truth table. A is complemented before it enters this gate and B is complemented before this enters the gate. See, we have taken, see, when two or more gates are used, these are called as the combinational gates. I have used two AND gates here. We have two inputs, that is A and B. Suppose this is A and B I will take. First we will complement one input here and I will take A and I will make this enter the next AND gate by complemented. B is complemented here, A is complemented here. A enters directly here, B enters directly here. The combinational output of both the circuits will enter the OR gate. OR gate is addition. AND gate is multiplication. I will write X. The output is taken here. Output is nothing but, see, A is entering directly from here and B gets complemented. So we can write A dot B bar. See, A is entering directly, it gets multiplied with B bar. B is getting complemented here, it enters as B bar. A dot B bar is coming out from here. Next, in the second AND gate, this AND gate is also multiplication. A gets complemented here, so A bar. B enters directly, it is A bar B. So sorry, B enters directly here. This is A bar B. A dot B bar and A bar B both gets added here. This is OR gate. This is for addition. So this combination gets added here. A dot B bar gets ORed with A bar B. Now the output, if you tabulate this separately, you will get this output. This you can take it as an assignment. You can try A B bar multiplication separately and A bar B ANDed or multiplied separately, and the combination can be ORed separately with a truth table. This will result in this final end result. So the circuit represents this. Let us take a single combination of data 0 0 and let us try whether we'll get this output or not. These inputs are 0 0, A and B both are 0. A enters directly here, here we have 0. B enters complemented, see, B is 0, when it gets complemented the result is 1. A gets complemented here, it is 1. B comes as 0 and enters here. AND gate principle is multiplication. We know 0 into 1 is 0. 1 into 0 is 0. Now it is addition. This is OR gate symbol. OR gate is for addition. 0 plus 0 is 0. So we got the output. Next set of input we will try for next set of input, that is 0 and 1. A is 0, B is 1. A comes directly as 0. B gets complemented as 0 here. 0. Next A comes here, gets complemented, turns to be 1. B comes directly as 1. 0 into 0, this is multiplication AND gate. 0 into 0 is 0. 1 1 here, this is for multiplication. 1 into 1 is 1. Now addition, 0 plus 1 is 1. Output is 1. Now next set, 1 and 0, it results in same value. Next we'll try for 1 and 1. A comes directly, see 1 and 1. A comes directly here 1. B complemented becomes 0. 1 into 0, 0. B coming directly here 1. A gets complemented, turns to be 0. 1 into 0, 0. 0 plus 0, it is 0. So finally we'll get a conclusion that the output of XOR gate is high when the inputs are unequal. We can simply say when the inputs are unequal, we'll get a high output. When the inputs are uniform or equal, we get the output low or 0. This is the main principle of XOR gate. We must remember this. The output is high when the inputs are unequal. Next, the XNOR gate. It is just the inverse of XOR gate. It is the exclusive NOR gate. It can be considered to be an XOR gate with output complemented. The output is high when both the inputs are uniform. The logic symbol is written here. It is same as the XNOR gate, one curve in front of the OR gate symbol, but there is a bubble in front which makes it XNOR. For XOR there is no bubble. For XNOR there is a bubble. Bubble says the output is complemented. That is all. We will get the exact result that is opposite of XOR gate. The circuit diagram is shown here. In the earlier case, that is XOR, only one of the input was complemented before it enters the AND gate. Here in this case, we are complementing both the inputs before it enters a set of AND gate. Here we use the same set of AND gate as XOR gate, same two AND gates, and finally both the results will enter the OR gate. For one AND gate, we are taking the data directly A and B. For the second set, we are taking A complemented and B complemented. The AND gate is for multiplication, we all know, and here also multiplication. Both gets added up to form the final output. A and B is entering directly. It is getting multiplied. A and B. We know A and B is A multiplication B. Now A gets complemented. A becomes A bar. B gets complemented after passing through this NOT gate, so gets B bar. So multiplication, A bar gets multiplied with B bar, so to form A bar dot B bar. There is considerable difference between A dot B whole bar and A bar B bar. One must understand the input A is getting separately complemented and B is getting separately complemented, and it then enters the multiplication operator, that is the AND gate, and hence the result is A bar dot B bar. If the output is complemented, it would have been A dot B whole bar. Now this A bar dot B bar enters the OR operator, and hence A dot B plus A bar dot B bar. This is the Boolean expression for XNOR gate. The output here we observe is exact opposite of XOR gate. I will write the output of XOR gate here. The XOR gate was generating output 0 when the inputs are equal. The output was 0. For equal input, output was 0. For unequal input 0 1 and 1 0, the output was high. Where XOR gate. In the XNOR gate, Since the output is complemented, we will be getting 0 turns 1, 1 turns 0 and 0 turns 1 again. So this is the output of XNOR gate. You can try verifying these inputs by substituting the value of A and B as given in the truth table and obtain the final result. Can take it as an activity. Now, observing the output carefully, we will observe the output is high only when inputs are equal input, that is 0 0 and 1 1. So when the inputs are equal, we are getting an high output, whereas in the XOR gate we were getting the high output with the unequal inputs, whereas in the XNOR gate we are getting the high output when the inputs are equal. This is called as logical equality, or XNOR is also called as the equality gate. We see one typical application of XOR and XNOR gate, that is the parity generator. Let us try to understand the fundamental concept behind parity generator. Before parity generator, what exactly is parity? Let us say there is a transmitter and receiver. We all know our mobile networks work wireless. A data is transmitted to the one tower and it is transmitted to the other tower, or for example when data is transmitted over cables, that is wires or bus, there is chance that the data sent, that is transmitter and receiver, suppose if transmitted from this end and receiving at this end, the data transmitted may not be same as the data received here, just because some foreign signals would have joined with the data that is sent. When we say foreign signals, that is nothing but noise. This noise must be avoided. We must ensure that the data transmitted is exactly received at the receiver end. Practically, this doesn't happen. We must have a security arrangement wherein to check the presence of any noise and hence to reject the data received at the receiving end. This kind of security arrangement is the parity generator. Here, parity is the extra bit attached to the digital data or the binary data that is attached at the transmission end and verified at the receiving end. If there is any error in the received transmission data, it is detected by the parity code. If there are any errors, the data is sent back to the transmitter and hence asked for the transmission of data once again. So this goes on as a iteration process until the data received is the same as the data sent. The binary data, let us say 0 1 1 1 0, this is the data sent at the transmitter end. This data must be the same at the receiving end. Suppose let us say the data received is something like this. This is called as error. Here the data sent is 10111, here the data received is 10011. So this is an error. The receiver end has to communicate back to the transmitter end asking once again the data to be sent. This work is done by the parity. What we are doing is we are adding one more parity bit. Let us say we have this data to be sent to the receiver. We will not be sending this as it is. We will be adding one parity bit. Just like we put an envelope to the letter that we want to send, we will be adding one more parity bit. Let us say I will add one more 1. This data will be sent and the receiver end will receive this data and we will check whether this is the same as sent by the transmitter. It will check for errors. This addition of parity bit work is generated by the parity generator. This bit along with the parity will reach the receiver. The receiver checks this data using parity checker. Transmitter generates a parity generator, uses parity generator. Receiver uses parity checker, checks the data. If there are no errors, it accepts the data. If there are any errors, it sends back the data at the receiving end with a message. Here the main concept is we are counting the number of ones in the message. The parity bit is the extra bit added to the word containing data in order to make the number of ones either even or odd. We are making the number of ones either even or odd. Let us say we have the data like this. We have two kinds of generator. One is even parity generator and odd parity generator. Here the number of ones is odd, hence the parity generator, that is even parity generator, will add one more 1 here in order to make this even. So the final data that will be transmitted is 1 0 1 1 and one more 1. This is the parity bit. This is A, B, C, D, and this will be parity bit added will be extra P. The final data that will be sent is A, B, C, D, P. This 5-digit word or 5-bit word will be sent to the receiver. The odd parity will add 0 because there are odd number of ones here, hence it will leave it 0. The even, there are two types of generator that we have seen, even and odd parity generator. When the data sent is of even parity, from even parity generator, the receiving end, that is the parity checker, must also be even. If the data sent is from odd parity generator, at the receiving end also odd parity checker must be there. A parity generator is a combinational circuit. We have seen when two or more logic gates are used, we call this as a combinational logic circuit. The circuit that generates the parity bit is called as the parity generator. The sum of data bits and parity bits can be even or odd. That is, sum of data bits and parity bits, we have seen the number of ones can be made even or odd. So in order to make it even, we are using even parity generator, or if we are leaving it odd, we are using odd parity generator. In even parity generator, the added parity bit will make the total number of ones an even. The total number of ones in this word, this is a word. Here the number of ones must be even, 1 2 3 4. Yes, it is even, so the parity bit will be 0. In odd parity, the added parity bit will make the total number of ones odd amount. If I use odd parity generator, the number of ones will be odd. Here it is even, the parity generator will add 1 to this. Extra 1 will be sent along with this word. Here we are seeing the even parity generator. The circuit is made up of XOR gate. If we recall, the output of XOR gate is high when the inputs are unequal. When the inputs are unequal, the output is high. Here we have taken 3-bit data A, B and C. That is, let us say 0 0 1 or 1 0 0, etc. The all combinations are taken here. The word length is of 3-bit. We are adding one more bit, that is parity bit. A, B, C we have taken here. From this truth table, observe here, this is even parity generator. It means the number of ones in this word must be even. If it is not even, we will add one more 1 and make it even. Now there are 3 zeros, no ones, so the parity is 0. Here there is only one digit, so in order to make it even, we will add one more 1. Here also it is only single 1. In order to make it even, that is 2, we will add one more 1. Here there are 2 ones, 1 1, so we will leave it 0 because it is already in even. Only 1, add 1. Here there are 2 ones, that is 2 ones even, 0. Here also there are 2 ones, the parity bit is 0. Here there are 3 ones, it is odd. In order to make it even, the parity generator adds 1. Observing the truth table, the output is high when the inputs are unequal. Here we are seeing the output is high when the inputs are unequal. When inputs are unequal, the output is high. This is the case of XOR gate. XOR gate, we have used combination of XOR gates here for 3 bits of data. Finally, we are getting the output Y, that is the parity. This parity data, that is A, B, C and Y, will be sent to the receiver. From transmitter, it will send to the receiver. Let us say this case 1, that is last but previous case 110, along with parity, it will be sent to the parity checker. Parity checker receives this. This is an even parity checker. It checks the parity in the receiver. Circuit can be an even parity. See, depending on the parity generator, the checker can also be even parity checker or odd parity checker, depending on the type of the data generated at the transmitter end. Parity checker has, in this case, 3 inputs along with even parity bit. These 4 bits are applied as input to the parity checker. We have discussed previously, ABC is the 3-bit data along with parity will enter the parity checker. The parity checker circuit is shown here. We will see the entire concept with the truth table itself. 3-bit data plus parity will enter the parity checker. It is an even parity checker. This checks the number of ones, that is 1 present in this word, if it is even or not. If it is even, it will generate the result 0. If it is odd, it will generate 1. 1 indicates error because it is a even parity generator. The parity generator has ensured that the number of ones that is present in the data is even, but if the receiving end the number of ones is odd, means it generates an error 1, that is parity error check. When there is error 1 is generated, that is there is an error, the data will be sent back to the transmitter. It will asking the data to be sent back once again. Here 0 0 0 0, no ones, so output is 0. 0 0 0 1, there is 1, only 1 odd, so error 1. 0 0 1 0, again 1, it is an error, odd number of ones. Here 0 0 1 1, even number of ones, so there is no error, error is 0. 0 1 0 1, odd number of ones 1. Here 2 ones 0, there is no error. Here also 2 ones, no error. Here 3 ones, even odd number of ones, so there is an error 1. So similarly it goes on. So in the last case you can see there are 4 ones, so no error, no error. So no error. When there is no error, this parity will be taken out and the data will be sent. The 3-bit data will be sent for the further use. Here in the previous parity generator case, there was 3-bit data and parity was the output. But in the parity checker case, all the 4 bits forms the input, that is A, B, C and the parity P. So all this enters the XOR gate and finally into one more XOR gate. All these are XOR gates in order to get the output. We will analyze this circuit for one example. Let us take an example 0 0 1 0. So A is 0, B is 0 and C is 1 and parity is 0. What happens? XOR gate, when the inputs are unequal, it results in output high. When the inputs are equal, it generates an output 0. Here inputs are equal, output is 0. Here inputs are unequal, output is 1. Again it enters one more XOR gate. When these inputs are unequal, 0 and 1, it results in output 1. So here we are able to see parity error check. It is giving an output 1. Let us see the last case, that is 1 1 1 1. What happens? 1 1 1 1. Equal inputs, XOR gate generates output 0. Equal inputs, XOR gate generates output 0. Again the inputs are equal, XOR gate will generate output 0. This is the parity error check. So this is one of the application of XOR gate. This can also be realized using XNOR gate also. With this understanding, we will see few multiple choice questions. The first question is, in an odd parity system, the parity bit is 1. Let us try to understand. In an odd parity system, the parity bit is 1 when there is an odd number of 1 bits in the data, when there is an odd number of data bits, when there is an even number of 1 bits in the data. In the odd parity system, we must understand the number of ones must be odd. If the parity generator adds one more 1 means there must be even number of bits in the data, even number of 1 bits in the data. When there are even number of 1 bits, then only the parity generator will add a parity bit of 1 in order to make it add. So C is the option. Second question, in an odd parity system, which of the following will generate a high parity bit? We have taken few examples, few bits of data. When the add parity system will add 1 to it, we have to understand again, odd parity system will add 1 only when the number of ones are even. When the number of ones are odd, it will generate the parity bit 0. Question is, when will it add 1? So simple, when the number of ones are even, it will add 1 to the bit. So here it is 2, here it is 4, here it is also 4 ones, so even. So in all cases, the odd parity generator will add a parity bit of 1. So all the above will be the answer. When the parity checker generates high output, it indicates. The question here is not about parity generator, parity checker. This has to be taken care. Parity checker generates high output. What does it indicate? The parity checker generates high output. The data received is same as data transmitted. Option B, the data received is not same as transmitted data. Option C, parity checker circuit has some error. Option D, none of the above. The parity checker will generate high output only when the data received is not same as the data transmitted, that is data error, when there is data error in the data received. Question 4, which of the following is referred to as an equality gate? We have seen the XOR gate generates the high output only when the inputs are unequal, whereas XNOR gate generates output when the inputs are equal. So option C, XNOR gate, is called as the equality gate. Which among the following is called as the universal gate? We have seen basic gates, AND gate, OR gate. AND gate is a basic gate, OR gate is a basic gate, XOR gate is an arithmetic gate. It doesn't come under universal gate. Universal gate is NAND gate and NOR gate. NOR gate is also called as universal gate. Option B is the answer. Question 6, a bulb can be switched on by closing any one of the two switches. A bulb can be operated by closing any one of the two switches. Then we must understand this is parallel connection. Any one switch can be operated to make this bulb glow. This is OR gate, OR operation. Na? So a bulb can be switched on by closing any one of the two switches. It represents which gate? AND gate. AND gate is not possible because AND gate, the switches are connected in series. That is, output is high when both the inputs are high. XNOR gate, it is not possible. XOR gate, it is not possible. The bulb can be switched on by closing any one of the two switches, that is only with the OR gate. So there is no options of OR gate. See, it is none of the above. So we thank you on behalf of LMS team. We will be meeting you in the third session of Unit 2 very soon. Thank you.